This is an Excel workbook to run Monte Carlo volumetrics. There are a few tabs in the workbook, as you can see here at the bottom, but it'll all make sense as we go along with the demonstration. We're going to start in the engine tab. What you see here is this table at the top where we have the parameter listed here on the column B, the unit of each parameter, and here's the value. Now, the value for each parameter is actually a formula depending on the distribution that you choose for each parameter. Okay, now these distributions are selected from a pre-existing list. So it could be constant, uniform, normal, log normal in 3 possible log normal ways, or triangular. Okay, depending on the distribution you choose, the function that applies, you see this is a VLOOKUP function, is explicitly outlined in this other column. Now, for reference, these distribution functions are actually listed on this key tab, right? So this little table here tells you this is just information, okay? It just tells you what is the functional form of each one of these distribution functions, okay? So constant is a fixed value. A uniform is expressed by a unif function, which takes two arguments, minimum and maximum, min and max. A normal distribution that takes as arguments sigma, so mean or standard deviation, as well as the minimum truncation value and maximum truncation value. There are three possible alternatives to express a log normal distribution. One, which is the log normal one, takes as arguments mean, standard deviation, minimum truncation, maximum truncation. That's it. The alternative way to express a log normal is by giving the P90 and P10 as well as the min and max truncation values. So it's just a different way for you to express a log normal with those different ways to pass inputs to it. And the third way is the same as the log normal 2. So you give it a P90 and a P10, but in this case, you don't pass min and max truncation values. Those are automatically truncated at P91 and P1. So those are not inputs, those are calculated by the function itself and automatically truncates at those two extremes. Okay, and finally, the triangular distribution, which takes as inputs min, max, and most likely. Okay, so this is just again an information table that tells you the functional form of each of these distributions. Now, all of these are functions that have been coded in the backend using inbuilt Excel functions. So all of these actually could be coded up directly here, but for simplicity and it's easier to audit the inputs for each function, I've coded up these as functions, and those are the functions that are called into this column when we need to actually write the formula for the distribution chosen by the user. Okay, so again, distribution is selected by you, and immediately the function is taken from that backend code. So for example, if the area I choose a log normal, it tells you right here that those are the inputs that need to be specified for that L normal function, and that is the one that is written here. Okay, now next to this blue block, we have these yellow blocks, which are the actual user inputs. Okay, and those will depend on the distribution chosen. Okay, so let's go one at a time and let's change so you can see in the table itself. First of all, you will notice this clear inputs button. So if we hit that button, all of these will be cleared. Okay, so I haven't passed any inputs, so you will see this obviously uh, value cells telling you something's wrong. Well, that's fine because I haven't passed any inputs to those functions yet, so the functions cannot calculate anything yet. But just to show you that depending on the distribution you choose are the inputs that become yellow cells, and those are the ones that you need to enter values in. So yellow cells are user inputs. So let's go. Let's say that we do choose a normal distribution for the area. I'm not going to debate which is the best distribution for each parameter. That's up to you. I just want to show you that depending on the distribution we choose are the user inputs you need to specify. So let's cover all of the distribution functions we have already discussed and listed in this preceding tab. So let's choose a normal distribution for the area. Let's choose a uniform for the thickness, a constant for the shape factor, a log normal 2, and log normal 3. So we cover all the log normal options, and a triangular for the BO. Again, I'm not discussing the merit of each of these distributions for each factor. I just want to show you the inputs that are needed to be entered depending on the distribution function you choose. Okay, and now we need to start passing the inputs for each of the distributions. So for example, the area, if we choose normal, as we discussed before, the inputs needed are those yellow cells, which is either constant most likely or mu, obviously depending on the function is the relevant label. So the normal distribution needs a sigma and a mu, or a mean and a standard deviation. So let's say the mean value of our normal distribution for the area is, let's say, 2000 acres. And let's say the standard deviation is 500. Okay, just whatever, doesn't really matter. This is just for the sake of the example. And we're going to truncate this on the low side, let's say 100, and on the high side, let's say 3000. Okay, something like that. Okay, let's go to the next one. Gross thickness in feet. This is a uniform distribution, the one we chose. The uniform takes mean and max. That's why those two have been highlighted in yellow. So the main value of our distribution is going to be, let's say, 20 feet. And on the max, we're going to choose, let's say, 60 feet as an example. Okay. Now, shape factor, we've chosen a constant distribution, so only a fixed value is needed, and that's why that one cell has been highlighted in yellow. In this case, it's the constant value, so that's the relevant label for that. And let's fix that at a 0.6. Okay. Now, again, as references in the key tab, I've left this, link where I took this snapshot from, which gives a bit of this is a historical page with typical shape factor values depending on the trapped geometry. Okay, again, this is just for you to have a bit of a reference to know, roughly speaking, what is the shape factor we should be considering. Now, backing out a couple of steps, this is a calculator for volumetric calculations done on an area thickness shape factor basis. So the GRV is it's actually here a calculation, but you could skip those three and actually express this with a GRV distribution. So the calculator itself could be easily adapted with a little bit of coding tweak in the backend. So instead of calculating the GRV based on those three inputs, just directly input the distribution of GRV, or you could go, if you have um, a, a structured top and you have the volume as a function of the contact depth, that function can be brought into here as well, and then you basically express your distribution on the location of that contact, or if you have um, the structure itself parameterized somehow, you can express the distribution uh, of that structure top, as opposed to uh, assigning distributions to these underlying three inputs. All of that is easily adaptable. Okay, but for the sake of this first iteration, this is what I've decided to do: area, thickness, and shape factor, and GRV calculated. Okay, so let's continue on. The net to gross, we've chosen a log normal, so that's the first way in which we can express a log normal distribution, and the inputs needed are mu, sigma, min truncation, and max truncation. So let's say the main is going to be a 0.7. Let's say the standard deviation is going to be 0.1, and the minimum truncation value, let's set it at 0.3, and the max, let's set it at, can be higher than 1, right? So that's it. Let's say that the porosity is also a log normal, but in this case, we're going to choose the log normal 2 function, which requires the P90 and P10 instead. So the P90 for the porosity is going to be 0.2, and the P10 or max is going to be 0.3. We're going to truncate this at 0.1 on the low side and at 0.4 on the high side. Again, just simple dummy input values. And the saturation of oil, this is an oil volumetric calculation. So the oil, again, we're going to choose a log normal, but in this case, we're going to choose the log normal 3 function, which only requires P90 and P10. That's why we have those two yellow cells only. And that is going to be, let's say, sorry, the SO, um, let's say it's 0.4 on the low side and 0.9 on the high side. No truncation values, again, remember, they are taken from the P99 and P1 percentiles from the log normal distribution itself. And finally, the BO, we're going to use in this case a triangular distribution. Therefore, the inputs needed are the most likely here on the first one. Let's choose a 0.2 and then a min and max. And let's enter 1.1 and 1.3 around the mid value. Okay, so now that we've done, let me just show you that in the case where you choose the log normal 2 or 3 functions, these are the inputs you are needed, but then there are these auxiliary calculations that are needed to uh, calculate the full distribution in the back end. So you can see directly here explicitly if those are your inputs, for example, P90 and P10, what would, in this case, the calculated sigma and standard deviation would be, and the extremes P99 and P1. Again, it's just an extra information layer for you. These are auxiliary calculations needed to compute the full distribution in the backend. Okay. Now that we're ready with all the inputs for each of our distribution functions, we're ready to write the formulas. We haven't run this macro yet, so if you step on these cells, you will see that the functions may have not been updated until we hit that. Okay, now you will see that these functions, x normal is that function, unif is that function, L normal is that function. Let's, for the sake of just demonstrating this one is a log normal 2. If I change this to a constant or a uniform, this one still has the log normal 2 because I haven't rewritten this. Okay, so log normal 2 is the one we had before. Okay, so until you hit that right formulas, these ones won't be updated. Okay, so you need to hit that button after you've selected the distribution for each parameter and all their inputs. Okay, so now that we're ready with the formulas up here, now the calculation can be actually conducted. And you can see here for easy auditing, the formula has been written using cell names. So you can see immediately what the formula is. And this obviously uses the ability that Excel has to name cells. So GRV is calling for that there. It's called GRV. That is called net to gross. Poro is that one. So you can name cells in case you didn't know this. And after you name cells, you can actually use those names in formulas, which makes it much easier to audit. All right, so we have our STOIP calculation here in this cell, and now we are ready to run our Monte Carlo simulation. What this macro does is it runs as many times as you express here in this number of trials cell, and in the back end, it runs this multiple times in each iteration, assigning a value for each parameter from within the distribution. That's what it's done in the back end. Okay. Now, before doing that, let me explain to you what this little thing does here. So if you untick that user dependencies box, all of these parameters are considered to be independent from one another. Okay, so all of those parameters are sampled using their distributions and ranges independently. All right, whereas if you use dependencies, all of these parameters are sampled from within the ranges and the distributions, but honoring a user-defined correlation strength between pairs of parameters. So if you use dependencies, you need to go to a tab where you specify the strength of those correlations. This is what this button does. It sends you to the correlation tab. And here we're going to specify the strength of the correlation. So let's say that you want the porosity and gross thickness to be positively correlated. Okay, now by the way, back to the key tab, I also have a bit of a reference or guidance as to what parameters could be considered to be correlated. Positive correlations here and negative correlations down here. Again, it doesn't need to be the case. You may have some other information in your particular case. This is just rough guidance. And also, I have a bit of an explainer as to how that correlation calculation is incorporated into this calculation engine. The correlation is using a Pearson correlation coefficient, and the strength of the correlation goes from -1, which is a perfect negative correlation, to +1, which is a perfect positive correlation with a value of 0, meaning that there's no correlation between the parameters. Okay, and this is how this is implemented, which is in simple words, it means each parameter is sampled from within their distributions, from within the ranges and with their distributions, and after they're sampled, the sampling is reordered in such a way as to respect the strength of the correlation specified by the user. Okay, so let's go back to the distribution to the correlation tab, and let's say that we want a very strong positive correlation between those two parameters, porosity and thickness, and a rather weak negative correlation, not very strong. Okay, let's leave it at, let's change it to -0.3. So strong positive correlation, rather weak negative correlation between those two. Okay, or even a little bit weaker. Okay, remember 0, no correlation, -1, perfect negative correlation. I just want to show you both positive and negative, but also a very strong correlation and a rather weak correlation. So let's leave those two. And after we've selected those two, we're going to go back to the engine. This is the output after we run the Monte Carlo engine. So for now, this is the input. After you've selected those, in this case, those two, it could be any other, right? Back to the engine, okay? And remember, you need to have that hit for the engine to consider those correlations. So we're going to do both. Let's do one first without dependencies or correlations between parameters, and then we're going to repeat the simulator with dependencies or correlations between parameters. Okay. Now let's leave this at 1,000. It could be anything. It could be 100, 500, 1,000, 10,000, whatever. Obviously, the greater this number, the slower it will be, but the more granularity in your distributions. So let's leave it as 1,000 for now, so you can see, and also you can gauge the speed of the underlying engine. So I'm gonna hit this button, and the engine is going to start running, and you can see at the bottom the status. So right now, trial 40 of 1,000. So you see the speed at which this progresses. It's running the Monte Carlo. We have no dependencies here, and you can see also visually at the top here the values that each of these parameters is taking in each of the individual trials or iterations. So again, this is what the macro does. The macro runs a cycle this many times, and in each cycle, each parameter is assigned a value taken from the distribution chosen by the user from within the ranges specified by these parameters. Okay, all of this happens in the backend. The user doesn't need to go there. The user only needs to select the distribution function for each parameter and the inputs required for each one of those distributions, and then choose the number of trials and whether or not to use dependencies or correlations between parameters. Now we're running the case in which we don't use dependencies, so all parameters are sampled independent from one another, and we're about to hit the 1,000. See the status at the bottom. 30 more and 1,000. Okay, now it's thinking, and it tells you Monte Carlo complete. Okay, it's done. Okay, now immediately you can see here that this is the STOIP distribution resulting from those parameters. Okay, it is a log normal. Visually, you can see this is a log normal because this is what the central limit theory tells you. When you multiply dependent parameters, regardless their individual distributions, you end up with a log normal distribution. And this is underpinned by those 1,000 trials or runs. Now, in this case, in this plot you see here on this very tab, I've highlighted in green red and blue, the P90 or low case, P50 or best case, and P10 or high case. And because this is taken from this table here, which specifies the bin, the frequency, the probability distribution function, and the cumulative distribution function on the right axis, this is a bracket. So there's no value in the table itself that pinpoints the exact P50, P90, P50, or P10. Rather, I just highlight the entire bin or the bracketed range where those metrics do fall, right? So it's obviously there's a range here, but the P90 is within that range, P50 is within that range, and the P10 is within that range. So as opposed to the exact point, this tells you the bin where those metrics fall. Okay, but in the table itself, you can see the precise value. That's the purpose of this table under the distribution. Okay, now after you've seen here the STOIP distribution chart, the table and the summary table, you can move yourself now to these two tabs. First one, in the correlation tab, now you can see the output. And this is a helper for you to visually see the correlation between pairs. So the way this works is first, we're going to calculate the correlation heat map. So it tells you how these correlations ended up as a result of the values sampled. This is a symmetrical matrix, of course. So that's 648 between GRV and area is the same one between the area and GRV. That's why that value is equal to that value. That's diagonal. And so you don't need to read both sides. And it tells you the strength between the correlations, and this is colored uh, with a color scale. That's why it's a heat map. So because we chose not to use any correlations or dependencies, we would have expected to have weak correlations between all parameters. Okay, so this tells you the actual correlations that resulted after all the sampling. Okay, if we select any two parameters, let's choose those two. Sorry, let's just change to any other, like net to gross and thickness. And after you select those parameters, you update the chart, and that's the crossplot between those two. It tells you it's all over the place. There's no direct correlation. So gross thickness and net to gross. So that's gross thickness, and let's go to the net to gross. It tells you it's a weak negative correlation in terms of the one parameter, but you can see from the crossplot, it's really a cloud of points. It's all over the place. There's no correlation. So it's just two ways. And this one doesn't tell you much. This gives you the detail. Let's have a look at this one, which seems to be a strong positive correlation, GRV and gross H. So let's select GRV here and gross H, cross plot. And indeed, there's a bit of a positive correlation, and that's obvious because the GRV here is not a parameter independently sampled. It's indeed a calculation that depends on that. So you would expect the GRV to have a correlation with all the preceding parameters that feed into that calculation. Okay, so this is obviously expected. So you wouldn't want to cross-plot the GRV because it's not independently sampled to prove or disprove whether your input correlations were honored. So let's choose another one. Let's choose SO and BO. And if we cross-plot that, again, it's all over the place. There's no correlation between those two parameters, BO and SO. So BO here and SO there. So as in this case, as characterized by this one Pearson correlation factor, is a very weak positive correlation. Doesn't tell you really much. There's no detail there, it's just one value. But here you can see in the cross plots, it's scattered all over the place, so there's no correlation. So it is acting as we expected because we chose not to use parameter dependencies. All right. So again, this is just for you to visually inspect the output after sampling all those parameters. And the next tab is the distribution tab, which gives you the ability to inspect one parameter at a time. So if we chose area, what this tab does is two things. First, it brings you up here, basically the section of the input that belongs to that, right? So if we chose area, normal, 2500, so we go back to engine, normal, 2500. So it just right here just for you to not to have to go back to the input tab, just see it here. This is what we chose as input parameters for that, and this is what resulted as output after the Monte Carlo engine sampled that distribution. So you visually see whether the distribution is according to what you wanted, as specified by the inputs. So this kind of looks like a normal distribution, but we truncated it too soon. This is what's showing here. So we truncated it at 3000. That's why it doesn't go beyond that. The mid value is somewhere here. You see the mean is 2000. Okay, seems to be all right. And the low side, we truncated it at 100. So it's way too far to the left compared to the high side, which is close to the mean. Okay, so you see here that visually the distribution resulting after running the Monte Carlo engine is actually honoring what we wanted as expressed by our inputs. But also you have this table here that now summarizes the metrics out of this output distribution. So the P90 is 1300, so somewhere there in green. P50 around the 2000, so that's that yellow, that red dot there, and the P10 or the high side is 2600, that blue node there, 2600. So again, this is an opportunity for you to inspect one parameter at a time and whether compare the output distribution and see whether this actually honors your inputs in terms of the distribution you chose and the actual inputs of that distribution. Now, you will notice the difference between this one here and that one there. These are dots. So this is because I've actually, as opposed to this tab where I've taken the bracket where the metric belongs in from this table, here I've drawn. So these are drawings. So this uses shapes in Excel to draw a shape, a circle, on the coordinates of the chart that belong with those exact underpinning metric values. Okay, so I presented both ways, which are the tools you have at your disposal in Excel, as opposed to going down the path of building, other more precise charts using more sophisticated charting packages. This is just Excel simple charts. In this case, I'm overlaying shapes drawn on the chart at those exact coordinates. In this case, a little bit more. Um, it's values taken from the bins themselves that define the distributions. Okay, but here again, you go one parameter at a time. Gross thickness. We had specified as inputs for this to be a uniform distribution with 20 and 60 as values. That's the uniform distribution there, right? Between 20 and 60. So that's good. And you can see the metrics out of that output distribution. The low side is 24. The high side is 56. Those are P90 and P10s, which are not the same as the min and max 20 of 60, but you can see those dots there. So it's quite honoring what we wanted, right? The next one is the shape factor, which in this case does not have a distribution because it's a constant fixed value, so nothing here is important for it. The GRV is a calculation, so there are no inputs for that. And as you can see, for the same central limit theory, or theorem, I should say, this is a log normal distribution with those three P90, 50, and 10 metrics. And net to gross, we want it to be a log normal distribution. You can see it has a bit of a tail, but not long enough. We're truncated it at 1. The range is quite narrow, so it's difficult to fully express a log normal shape, if you will. But you can see the underlying metrics P90.58 is P50 and P10 in this case because we expressed this log normal distribution with these inputs. It's difficult to compare because we have no notion of those three metrics, but you can see here the mean and sigma, 0.7, that's the output out of the distribution, is exactly the 0.7 we have here, and 0.1 is the sigma, exactly the one we had there in the input table. And the truncation values 0.3 and 0.1, 0.3 somewhere here, and the 1, sorry, not 0.1, 1 over here. So yes, the output distribution is indeed honoring our specified inputs. The porosity, we want to be a log normal. Again, it has not such a long tail, still a narrow range, truncated at 0.4 and 0.1 on the low side. And now we did express this function with P90 and P10 inputs, 0.2 and 0.3, and the outputs P10 and P90, P90 and P10 are indeed 0.2, that's the P90, and 0.3, that's the P10. So again, it is honoring our inputs. And the next one, saturation. We wanted this to be a log normal. Now this one has a fully developed log normal shape. This is expressed only by the P90 and P10. We can see from the table P90.4 is over there and P10 is zero point 0.9. So it is honor. Again, you can see that the values from the chart do correspond to the values outlined in the summary table with the metrics. So again, you're checking that the output did indeed honor the inputs. The BO, in this case, is a triangular distribution. That's our triangle. We wanted the most likely value to be 1.2. You can see there at 1.2 and also on the table 1.2. The min and max 1.1 and 1.3. Min and max are not the same as P90 and P10, which are the values in these two extremes in the node on the chart and in the table. We can see the main is 1.1 and 1.3 up here. Okay, so that's basically the extreme values. Those are the ones you feed into the distribution. And finally, the STOIP, no inputs, obviously. This is just the final calculation. And this is the same chart as the one we had already seen, except that this has, once again, the bracketed range where each of the three metrics falls, whereas here is the precise location. So this is a shape drawn on top of the chart with those three values. All right. So this is basically how the tool works. As a summary, you have the main engine tab where you specify the distribution function for each parameter, the inputs in the yellow cells, you write the formulas here, you select the number of trials for your simulation, you run the Monte Carlo simulation, and then you inspect the output correlations, make sure that the cross plots are in line with the correlation strength you wanted. And the distribution tab is where you inspect one parameter at a time, making sure that the output distributions are honoring the inputs you selected for each. I did mention that the full distribution for each parameter is listed on this table you see here to the left. So here is the number of trials. We did run in this case 1,000 trials. Okay. Now all of this uh, is coded up in a VBA in the backend, but you don't need to go there. You just need to operate in these tabs here. The key tab has some additional information with references to what we're using in the tool, and the README tab gives you a bit of the sequential workflow through the tool. Okay, that's pretty much it. Now, what is pending is going back to the engine, and in this case, let's use dependencies. Now, I'm going to leave this running just for you to notice that this one is going to be running, but the entire process is much, much slower because there are various steps involved in completing the Monte Carlo simulation. The first one is sampling. Okay, now we're sampling each parameter from within the ranges using the distributions selected. Then there needs to be a resorting or reordering of those individual samples as to honor the strength of the correlations specified. And that's going to take much longer. So you have to be aware that you are going to use dependencies. The process is going to take much longer. So you can just leave this running, go for a coffee, and come back later. So I will cut the video now, and I'm going to come back when this is finished just to inspect the output. Okay, now I'm back. The Monte Carlo simulator has finished, and this is the STOIP distribution that resulted from all those inputs. You can see visually the log normal distribution shape on this chart. Again, those are the three brackets with the P90, 50, and 10. Same deal as before, you can go to these other two tabs to inspect the outputs. So in this case, we're interested in now seeing if the dependencies we specified have been honored. So if we go to the correlations tab, we want to inspect porosity and gross H. So first of all, let's just use those two as examples. Let's recalculate the correlation heat map. And again, immediately I can see that porosity and gross H here as a factor is very close to that 0.9 we had specified as inputs. And the minus 0.2 between the SO and poro, so SO and poro minus 0.188. So those two actually, those are the output correlation strengths or Pearson correlation parameters, are very close to the ones we had specified as inputs. So that's good. And also visually inspecting the cross plots. Again, if we start with those two and recalculate the chart, those two aren't supposed to be correlated, SO and BO. We didn't specify any correlation strength parameters between those two. So as an example, that scatter cloud reflects that there's no such correlation between those two. But if we select those two, porosity and gross H, so let's select porosity here and gross H here. Let's update the chart. So there we go. We have a strong positive correlation between those two parameters as seen in this cross plot. And likewise, let's go now between those two, SO and Poro. So let's leave Poro there and SO now here. And let's update the cross plot. And in this case, because it's a weak negative correlation, you can see kind of, in the cloud, you have to read between the lines. That is the actual Pearson correlation factor value out of that cloud. It is a weak correlation for sure, okay? But again, you have these two tools at your disposal, a cross plot between parameters and the heat correlation map here. You can compare whether this actually honors what you wanted as expressed in this input correlation matrix up here. And then again, if you go to the distribution, you can inspect one parameter at a time. Let's say Poro. And again, you have the snippet with inputs you had specified for that parameter. And this is the resulting distribution, in this case, a log normal. The BO was, as an example, a triangular. So there you go, that's your triangle. So again, you can go one by one and you have the full table with all parameters and all, in this case, 1,000 trials here. Here's your selector and then your input little table snippet, the output distribution, probability distribution function to the left, cumulative probability or cumulative density function to the right, summary table with the key metrics. And these are the bins and the three values, which are the ones indeed underpinning this chart. So that is the tool. Have a play and let me know how you go. Cheers.